Okay, good morning all, and welcome to our concrete webinar. My name is Marit, and I'm currently a part of the customer success team for over 2.5 years now. And today I will be guiding you through our new developments and improvements, which you can find in concrete. If there are any questions now or later on, do not hesitate to reach out to us via our support contact information, or to let us know via the chat here in the GoToWebinar interface. Now let's start by taking a look into our topics of today. What's new in this case? We improved our provided reinforcement templates for 2D elements with some extra options. We will check the new nonlinear analysis for reinforced concrete structures. We check on what is modified for the method analysis of the second order effect, and we will take a look into the improvements for the code-dependent deflection analysis there. So these are the 4 topics we will be discussing today. Now, as said, I would start with the improvements for our reinforcement template for 2D elements, which you can find for both walls and plates in SCIA Engineer. Now, when comparing these templates to the ones we had in previous versions, you will notice we actually improved the possibilities for the additional reinforcement. The basic template is exactly the same as before. You will choose a fixed diameter with a fixed spacing for each direction and for each of the surfaces. This change is specifically found for our additional reinforcement. Before, you could choose between 3 different options. You had a fixed type, where you chose a fixed diameter and a fixed spacing for the additional reinforcement, or you could create a list based on different diameters with a fixed spacing, or a list based on a fixed diameter with a few different options for the spacing there. Starting from version 24, you will actually be able to combine these different lists to create more options. And you will be able to sort this created list in a few different ways. First of all, based on the minimum area. Second of all, based on the minimum diameter. And lastly, based on the maximum spacing. So the biggest improvement there is that you can create a list based on the minimum area. Now, to show this a bit more in detail, I suggest we go to our software, and I created a simple example where we can take a look into our concrete settings. Now, as usual, if you wanted to check the concrete settings and your provided reinforcement templates, you can find them underneath our reinforcement tab here. I did open the complete setup for my concrete settings, so everything was visible there. Now let's take a look into the template of our plate here, and you can open it as usual with the green dot. Now, by default, the template plate will already be created. The 3 other options I created here were specifically made for this example, but I will tell you more about that later on. Let's take a look in this template specifically. So as said, the main principle of this template will remain the same. We have our basic reinforcement template where you define a fixed diameter and a fixed spacing, and the difference is found in the additional reinforcement template. Whenever you open the drop-down menu now for the diameter or the spacing, you will see exactly the same menu. You will see a list of the selected options that we have right now. So my selected spacing and diameter options are shown here, and they are shown in the order that you have chosen. So right now they are ordered based on the minimum area. If I would modify this, you will see that the list will change its order. Now, I can start adding new options to this list, and I can do this in two different ways. If I would like to add diameter 12 to this list, I can use a semicolon in my edit box here above, and it will add this specific diameter like that, but it will also add this specific diameter with all the available spacing options. So I see now I have added diameter 12, and the spacing of 400 is added, as well as 300, 200, and 100. So all these options are added immediately when I use a semicolon as a separator. There is a second way to add different diameters with a fixed spacing, and that's when I use this drop-down menu to select a specific diameter with a spacing. So let's say I would like to add a diameter 16 with a spacing of, for example, 400 in this case, and I click on Add. You will notice that only this specific option is added to my list. All other spacing options for this diameter are added as well in the background, but they're not toggled on. If you would like to toggle those options back on, you can find them by toggling off this option here, Show Only Used. Once I toggle that off, you will see that the other options of diameter 16 with their spacing are shown as well. And you can choose to toggle them on or off based on your liking. If you want to save the changes you made here, do not forget to click on OK on the bottom here. If you close the drop-down menu before, you will remove all your settings that you changed here. So those are the two ways you can add your options here. Now, what have I created in this model? Well, I created 3 of the exact same plates with some supports below and the exact same surface load on these plates. I did attach a specific template to each of these plates with concrete data. If I select one of them, the first there has a design template where it is sorted based on the minimum area, and I've chosen some diameter and spacing options. I created the exact same template for my other 2 plates, but there I've chosen a template where the order is modified based on the minimum diameter or based on the maximum spacing. So the order for which the additional reinforcement will be added will be different for each of these plates. Now we can take a look into what that difference could be here by taking a look into our reinforcement design. So let's take a look there. I will refresh my result for that specific load case, which just contains a surface load, and I will just check my direction 1+ in this case. Now, I did create a small image where the order of each list is shown, so you can see the difference in the color palette which is used for each plate, but you can also see the order here below. On the left, we sorted based on the minimum area, and you see we will start with diameter 8 and a spacing of 300, move forward to our turquoise area where a spacing of 8 with 200 is used, and so on. So we see next up in the green zone here that diameter 12 with a spacing of 300 is used, and so on until it reaches the end of our template. Now on the second template, we sorted based on the diameter. So you see the list is different. Instead of going to diameter 12 with a spacing of 300, he actually starts by going to diameter 8 with a spacing of 100 in the yellow zone. Afterwards, we see that he will skip the option of diameter 12 with a spacing of 300 for this plate, since the area of reinforcement is lower than the option above, of course. and you will just finish the template as usual. And for our last plate, we see that the order is different as well, and you can see the difference in the color template there. So that's it for the template. You should be able to see these differences based on the order that you choose. So next up, we were going to discuss our new nonlinear analysis for reinforced concrete structures. Now, this functionality will be called reinforced concrete material nonlinearity, which you will have to toggle on in your project data. By activating this property, you will be able to change your material properties and define a nonlinear stress strain diagram for your concrete materials or for your reinforced steel materials. Now, for concrete materials, you will have the option to take into account Mazar's law and use some predefined stress strain diagrams with or without tension resistance. For our steel materials, you will be able to use the elastoplastic law with or without kinematic hardening. As well as those predefined options, you will also be able to manually define a stress strain diagram based on your input. You will be able to create those materials for both 1D and 2D elements, and you can perform this nonlinear analysis for both elements with or without reinforcement. The most important part there is that the reinforcement that you add needs to be user reinforcement. So just the templates will not be taken into account. Other than that, this is also compatible with our general plasticity functionality. So if members made of another material than concrete are present in your analyzed structure, the calculation employs the linear stiffness or plasticity whenever you enable this, which means that it is, of course, then compatible with that functionality. Now, I suggest we take a look into one of our examples to just show over this functionality and where to modify our material properties. Now, first of all, I said it before, you will need to activate this functionality in your project settings. So first of all, we check our functionalities. Nonlinearity is toggled on first, and afterwards you will be able to select your reinforced concrete material nonlinearity. Once this is activated, you will be able to find a new property in our library here in the material. So let's open our library there, and I see a few materials here are already modified, but let's start with choosing one arbitrary option here. Now we activated our functionality, so we see this new option here below, material behavior for nonlinear analysis. I now selected a concrete material, and I can change it from elastic to isotropic damage by Mazar. Once this is activated, you will be able to create a stress strain diagram. Now, as said, we have some predefined options. You can use bytecode without tension part, bytecode with a tension part, or you can create one yourself. Now, whichever option you choose here, you will be able to make this stress strain diagram visible. If you click on the three dots right next to diagram, you will be able to check what you have set here. Now I've chosen bytecode without tension part, so we see it ends here on the left in 0. If we would modify this to with tension part, we would see an addition here to the left of our diagram. Now we have some few other settings that we can make whenever we choose one of the options by code. The first one you find here is type of values. There you can choose if the characteristic mean strength values are used or if the design values are used. And these are the values that you will be able to find in your material properties as well. So we find here our mean compressive strength and our design compressive strength. And here as well, if we would change this to design values, you will see that this other value is used, while when we selected the characteristic mean strength values, then we saw value of 24 was used there. Other than that, you can also change the type of diagram from parabolic to linear constant whenever you need to. Lastly, to create this predefined strain stress diagram, you can consider the creep effect. Now, if we toggle this one on, you will get a second option to define this phi factor, and this will, of course, have an influence on your stress strain diagram. Your stress strain diagram will be multiplied by a factor of 1 plus phi. And we will see that here as well. Before, my strain was, if I am correct, somewhat around 35. So you will see this effect there as well. Now, what if you want to create your stress strain diagram manually? Then we modify this option here from by code to by user definition. Whenever you do so, you will have an extra option here, user definition, to open a new dialog there. On the top, you can start adding some options when you'd like by right-clicking, and you can just choose to insert new lines there. I'm just going to add an arbitrary value here, and once you created 2 lines, you will see your stress strain diagram is shown on the bottom there as well. You will also be able to paste some columns from Excel as well. If you right click, you will see you have the option to paste all. Now, other than that, if you want to start from a predefined stress strain diagram, that is also possible. On the bottom there, you can create one from default. And there you will see that we have the options that we discussed earlier. So the stress strain by code with or without tension, the different type of values, the type of the diagram, and then if you want to consider the creep effect or not. If I press OK, you will see that it will be inputted and that you can still modify each column or row. Now, an important part here as well is that you need to fill out your limit strain in tension and compression as well. So these options are added here to add the limit strain. Now, what is different here as well is that you can change what the end of your diagram looks like. Right now, by default, the option failure is chosen, and this will also be the option that is used for our predefined stress strain diagram. Failure will mean that your stress changes to 0 without increasing your strain in this case. The other options that you have here are yielding, where you see that our stress is continuous while increasing our strain, which is shown by the gray line here at the end, and continuous, where we just take a look into what the deformation is for our last 2 known points, and it will just move that forward continuously. You can change this for the compression side, but you will always also be able to change this, and you see it here for our tension side. So that is all possible there. Now, I have a small example with 1D element here. Right now, no reinforcement is added to this model, so they are only taken into account our concrete material here. Now, on the bottom row, I have used an elastic material. I've chosen a C20 25 if I'm correct, and I use the elastic material there. For the two top rows, I changed the material properties to use Mazar's law with or without tension. So you will see a difference there. Now let's take a look into our results without reinforcement first. We'll start our nonlinear analysis. I just created a nonlinear combination with some basic point loads and line loads in it. Now, if we check our deformation, we shouldn't see a lot of difference, of course, between all our options. We see, of course, that the elastic material deforms less than our materials above. And then we see, of course, the difference without tension. Then we see that the deformation is larger than with tension. Now, we do want to take our reinforcement into account, and as such, you need to add real bars as reinforcement. So for my second option here, I will be adding reinforcement based on our provided reinforcement template. Let's take a look in those results if we go to Concrete 1D and our reinforcement design, and I will check our provided reinforcement. I will refresh these results for a moment, and I will see all of them get the exact same reinforcement template. And to take this into account for my nonlinear analysis, I will need to use conversion for real bars to add the real bars in my model. Now you will see after I imported my reinforcement, you will see that the results of my nonlinear combinations are removed there as well. Now for the last option, I will use the second method you can use to input reinforcement. I will use the option here 1D reinforcement, which you can find in the input panel. If I scroll down, you see you have all these extra options, and I will use 1D reinforcement to add this to my element, just from beginning to end. Now I will just choose one of the default templates that are created here. Let's go with this specific template. It will be somewhat different than the reinforcement that I used on the 3 middle beams. Like that, I added it to one of those beams. If I would like to copy this reinforcement, we can by just selecting it and copying my add data to my other beams as well. Now I will need to recalculate my project to take this into account, and we can take a look into our calculation settings here as well. Normally, when you have activated this nonlinearity in the project, you will see that the average number of mesh elements is automatically set to 5. And if we go to our solver settings and go to the nonlinear properties, you will find out that Newton-Raphson is selected automatically and it will be grayed out. The number of increments and maximum iterations are also automatically set to 10 and 500. Now let's start our calculation. Again, it will reperform only the nonlinear analysis. And then we can take a look into our deformations again to check that the reinforcement is taken into account here. I will just take a look into the exact same results as before, and then you will see that we reduced our deformation, of course, by adding our reinforcement. This was reduced for our elastic elements as well, but also for our elements where we used Mazar's law. And again, you see the same deformation. With tension, we see that the deformation is reduced, while without tension, we see that our deformation is the largest. So that's the biggest difference there. Now, I do have an example for 2D elements as well, which should already be calculated. So we can just check the results there as well. Let's say we can compare our 3D deformation for the linear results and the nonlinear results here. Now, what do we find in this model? It does contain some columns and walls as well, but we will take a look into our 2D plates. Now, these plates already have defined reinforcement. I now selected one area of it, and the reinforcement is added both on the lower as well as on the upper surface. I just selected one of the examples here. This reinforcement is specifically created with the type 2D reinforcement. Keep in mind that 3 bars should also be supported here as well. Let's take a look into those results. I say we start with our linear combination, and let's check the deformation we find here is 10.5 millimeters. Our nonlinear combination consists of exactly the same combination factors, but then, of course, it will take into account our material properties. And there we will see a deformation of 15 millimeters is found. If I check my material properties one last time, we will see that we used a material type where we modified the material behavior from elastic to isotropic. So therefore, this explains why our deformation is larger than it was before. So that's a basic overview of our new nonlinear analysis and where to set this stress strain diagram. You will also be able to change the properties of your reinforced steel material. Now, this actually brings us a bit to the next part, since whenever you activate this functionality, you should actually toggle off your second order effect in the concrete settings, which can be taken into account for compression 1D members. And this is actually something that we did improve in version 24. Now, we did change some things about these concrete settings, especially for this method of analysis for the second order effect. We changed the parameters a bit. We sorted them in a way that they are sorted based on which methods they are used for. So a new subtitle, simplified method, and general methods are added here. What did we modify here as well? Well, before you had to manually toggle the simplified method on or off. We could not define it automatically. And that could be an issue, since if you set this parameter wrong for your project, it is possible that you take a second order effect into account twice. Now we have added a third option here, which is auto general. Whenever this is toggled on, the methods used for the second order effect will be based on the calculation settings that are used in your project. And I've added a small table here below, which actually shows when a specific method should be used. So whenever you use a linear combination, the simplified method should always be used, of course, based on the settings you have used it. Whenever you perform a nonlinear calculation with nonlinear combinations, it's necessary to check if one of the nonlinear properties are toggled on or not. What is checked for you? Well, it is checked if you use the reinforced concrete material nonlinearity, so the PNL option we discussed right before. It will check if you have toggled on the functionality geometrical nonlinearity, and it will check if your nonlinear combination has some global or bow imperfections defined. Now, whenever none of these options are toggled on or defined for a nonlinear combination, then the simplified method should be used there as well. In all other cases, when one or more of these options are used for a nonlinear combination, then the general method will be used. And this is also something that we can check in one of our examples as well. I just created a general example which just consists of one column with some normal forces to make sure it's a compression member and some shear forces in both directions. Now let's take a look into those concrete results here. I will check my internal forces for design. Now let's start by checking our basic bending moments. In this column, there we will notice a value of -72 kilonewton meters for this column. Now in my concrete settings here, I have used that method that we discussed now. Method of analysis is set to auto. So it should define for us which method should be used here. If we then check our bending moments for design for my linear combination, I should notice that my bending moment got larger because, of course, my second order effect is calculated with the simplified method. I did create some nonlinear combinations here as well. The first one does not have any bow or global imperfections defined. All other three do have or a global imperfection or a local imperfection or a global and a local bow imperfection. Now, all three of these options should result in using the general method instead. Let's check those results as well. If I go to my nonlinear combination, I expect that my first combination results in a similar result as my linear result. Let's refresh those. And I see here a small difference, but I do notice that my second order effect is calculated there. We should also be able to check this in our report preview, where we should find that our second order effect is calculated. So I see here first order eccentricity, and then here the second order eccentricity is calculated. Now for my three other nonlinear combinations right now, I expect that my simplified method is toggled off. And if I load the results for nonlinear combination 2 and refresh this, I should see that my design bending moment is lowered. If I check my report preview now for this nonlinear combination, we should see a note stating that the second order eccentricity is switched off. And that's because I selected the method of analysis to auto. We will see similar results for nonlinear combination 3, where I activated a bow imperfection, and for nonlinear combination 4, where I activated both of them. Now, other than that, right now we've taken a look into a project for which both functionality, geometrical nonlinearity, or my reinforced concrete material nonlinearity are toggled off. Once I toggle one of these options on, my first nonlinear combination should result in a lower result as well, since it will also toggle off the second order eccentricity. We will have to recalculate this for a moment, and then we can check the results for our first nonlinear combination. But since geometrical nonlinearity is toggled on, we should see that the second order effect is not calculated anymore. So let's go to nonlinear combination 1 and refresh those results. And before we got quite some high bending moments, and right now they are lowered. Check the report preview again to make sure that it's toggled off, and we should see a note here as well that the second order eccentricity is switched off. We can manually override this as set if you change this from auto to simplified or no, you are overriding this setting, but of course keep in mind that it's possible to take the second order effect into account twice. What is something else that we improved here in this menu is the parameters which will be used. We added an option to modify our C factor, which is linked to nominal curvature, or our C0 factor, which is linked to the nominal stiffness. Before, it was always automatically defined. You would use, for example, for our C factor, a factor 8 when a constant bending moment is found, and a factor 10 whenever the bending moment is different. Now you will be able to choose a predefined option to use the value 8 or 10, depending on the curvature distribution, or you can even choose a user value. And the same can be found for our C0 parameter. Now, to show that here as well, if we open our menu for the simplified method, you will be able to find these parameters here. By default, they will be put on auto, and you can just modify them and choose your factor here. So those options can be found. And if I switch from nominal curvature to nominal stiffness, you will see you can modify the C0 parameters, which will be used. The explanation of the value which is used for each option here can always be found here on the right when that helps you. If this is hidden, make sure to use the double arrow at the right there to make it visible. And this will also have an effect, of course, in your report preview when you would check it a bit further. So that's it for those second order improvements. Now, lastly, we're going to discuss our new code-dependent deflection analysis. Now, we did improve this analysis and made it more powerful and more accurate, because starting from version 24, we will be able to perform this analysis for nonlinear combinations of the type serviceability, which means that we can support nonlinear properties like pressure only and so on. We can take into account hinges, take into account eccentricities, which are used in your model modifiers, and orthotropy. Another thing that is improved is that before you could only take a look into your results based on the local coordinate system, and for 2D elements that also meant that you could only take a look into the local Z direction, which means out of plane deformation. Now you will be able to take a look into the results according to the local coordinate system, but also according to the global coordinate system. This also means that starting from now, we will be able to take a look into the in-plane deformation as well. Now, I do have a pre-calculated example to show this specifically, so let's take a look into that one. It's a general model. Well, we did add some hinges, some nonlinear properties, such as tension only, I think, actual force only, and the beam nonlinearity here is set to press only. And I will see here that my hinges here on top have a nonlinear property as well, where they are set to press only here. I think the other hinges onto D have similar properties. If we take a look into our code-dependent deflection, you will see that you will be able to choose your nonlinear combination now, or choose a class which contains nonlinear combinations. Let's take a look into those. I created a few there, I think 13 nonlinear combinations, and they are all from the type serviceability. Whenever they are from the type ultimate, you will not be able to select them for the code-dependent deflection. These are also the combinations which are added to my results class. So I do have added them here. Now the options below for your type of reinforcement are the same as before. You can choose required reinforcement, provided, or user reinforcement. This is the same, and you will be able to set your type of load for calculating the required reinforcement. Now, the other differences are, of course, found here below. Before, only the option local coordinate system for mesh elements was available here, and you could only choose Z direction for 2D elements. Only Y and Z were available for our 1D members. You see right now the option X can be chosen here, but you can also change your system to global. So let's start with taking a look into this deformation. This will look similar to what you were able to view before, only out of plane deformation for our walls. Let's change it then for a moment. Let's choose our system and set it to global. And then keep our direction to Z. We can refresh our results and you will see a difference there as well. Now you will notice that our pressure only hinges are taken into account as well, depending on, of course, on which plate we're taking a look into. So you should see these differences whenever you open an older project as well. They should be taken into account now. So those were all the new developments and improvements that I wanted to discuss today. If you have any questions, of course, again, do not hesitate to reach out to us via our support contact information.